Hi, this is Justin Mansell from Active Optical Systems, and this is a tutorial on how to use the AOS AO simulator. So the first thing you want to do to get the AOS AO simulator is to go to the AOS SharePoint site. There's a link on the AOS website directly, but you can see the URL up here. It is https://sp.aos-llc.com/site/portal. You'll have to have an account on there, and if you need one, send us an email. We'll get one set up for you. And then you log in, click on Downloads, Export Controlled, Software, Utilities, AO Simulator, and you can download the latest version of the AO simulator. If you have a previous version installed, you will have to uninstall that before installing this new version. I've already done that and created a shortcut to it on my desktop here, which is done by default, so I can run the software. What you'll see when it pops up is the input tabs on the left side, and then on the right side all of the output tabs. So the first thing you want to do is establish an adaptive optics overlay. The units in this are all specified in millimeters. I am going to try to do more like a 7x7 mirror here. It's set up right now because of the clipping to a 5x5. So let's increase the clip diameter to, I will say, 40 millimeters. And that's a little bit better. I still think this is the wavefront sensor, which is this circle here, and the circles specifying the subaperture locations is a little too big. So I'm going to go in and to the wavefront sensor specify the clip diameters a little smaller than that. Let's say 30. There we go. Now we're pulling it in, and the reason for doing that is that if you want to get good performance for things like Zernike terms, you're going to want to have actuators outside the periphery in order to get better edge control. Okay, back to the DM side. It's set up as default to come up into Gaussian influence functions. I'm going to make that plate for what we're doing because it's a little more accurate. Gaussians are good because they're very fast to calculate. Plates take a little longer to calculate. You could also do membrane, piston, and piston-tip-tilt. This specifies the nominal max throw of the DM, so when you see normalized command plots, they're specified relative to this max throw. I've told it to draw a 3mm box around each actuator, so that it makes it a little easier to see where all the actuators are. There's a whole group box here that specifies slaving. We're going to skip that for today since we're not looking at slaving any of the edge actuators at this time. This is the wavefront sensor configuration tab. You can do things like show where the indices of everything are, which makes for a very cluttered plot, so I usually turn that off. You can specify the spacing between subapertures and the offset, and if you want to just do generic free geometry, you can click on that and it will produce a free geometry version. I'm going to do over-resolved wavefront sensing for today, and I'm going to add an offset so that I don't have a subaperture on top of any of my actuators. Now I can go in and look at the clip diameters. Those look okay. We've already tweaked that up. You can have it draw a box on here. So let's say I did a 2.9mm box on each of the subapertures. You can see how that plays out. You can also tell it to make a wavefront sensor image out of this. So I can click on this button after specifying these parameters. And since we were running out of tabs, I decided to put it into the Matrix tab as one of the various matrices that can come down. So this is an image of that wavefront sensor on this false color plot. Okay, go back to phase control on that and go back to the overlay here. So now that I have a DM specified and a wavefront sensor specified, I can specify an aberration that I want to fix. The default aberration when you boot this up right now is for focus to come up, but you can do any of the Zernike terms or combinations of the Zernike terms. So let's say I wanted to add a little bit of 90-degree astigmatism. I can hit generate Zernike, and now it's starting to look like a cylinder term after I've added some astigmatism to the focus. That makes sense. I'm going to specify the Zernike diameter to match my wavefront sensor diameter, which is 30, and 30mm aperture diameters, and I'm just going to leave that clip way out there. Okay. So you can specify Zernike's. You can also tell it to do Kolmogorov spectrum turbulence. And so it'll go through and randomly generate turbulence with this R0 value. Can make that a little bigger. Let's see. I'm going to bring the aperture back up a little bit, though, in case that I want to use a beam that's a little bit bigger. There we go. And now we can keep clicking on this and generate different random realizations of turbulence. You also can load your own aberration. The thing I'll caution you about is making sure that you've specified the mesh size. This is the number of points across it. It's only designed right now for powers of 2. And the mesh spacing appropriately. You can unclick auto and specify this manually. I leave it in auto because then it just picks what it thinks the best spacing is going to be. It does a pretty good job of that usually. When you're loading an aberration, you can also tell it to multiply that aberration by a certain scale factor in order to increase or decrease the amplitude of the aberration. Okay, so now that we've got an aberration, we'll just stick with this Kolmogorov spectrum turbulence for the moment. We can do adaptive optics. And you can see that I've got no data in the fit right now. I can have it try to fit based on a certain amount of based on phase, and so that it will go through and generate the influence functions. And let me show you that. Here are the influence functions that it generated in a plate type pattern. This center influence function on this one looks about like I'd expect it to. It's nominally Gaussian. It's got 4 little divots to the side that represent the bending mode between these basically adjacent actuators. You can actually make a movie of that if you'd like, and it stores that in the output directory specified in settings here. Also tells you where that is, and so it made a little movie. I will go to this now, sort on date modified here, and see if I can find that movie. It's going to be up toward the top here. There it is. So this is the movie of the influence functions, and this is nice if you're trying to make a presentation of the DM's capability. So this is that movie. Okay, and close that now. Go back to the AO simulator. After it generated the influence functions, it created a phase control matrix and phase, well, actually, it's a phase poke matrix first. And so this is a sampled version of the phase at each of the sub-apertures, and then it tries to invert that using single value decomposition. The SVD gains span a little over an order of magnitude, so we might have some goofy things happening at the edge. And then this is the inverted version. This looks like I've got a few sub-apertures that are especially weak. Let me take a look at the overlay. Yeah, and it's probably some of these, it's not the sub-apertures, it's probably some of these actuators toward the edge that don't have very little influence on these sub-apertures. And that's okay for what we're doing. And this might be an instance where slaving would help us. But for now, let's just try removing modes. I don't like to remove more than about a mode typically from this, maybe 2. But if I don't have time to set up slaving, sometimes I'll get lazy about this and start pulling modes out. So this is starting to look like I'd want it to. It should be a matrix that looks kind of like the transpose of the poke matrix. So this is a diagonal-ish kind of matrix. A lot of diagonal content, not a lot of off-axis content. I'd expect something similar for the control matrix. You can see it's starting to happen, but we still have these large streaks here. Again, this is an instance where probably slaving would help us a lot. But let's take a look at the aberration and then the fit to that. These look very similar in low frequency space. Residual looks pretty good except for at these edges. One way I like to visualize that though is to take a look at the compensated far field. So this is the compensated far field, and to give you something to compare it to, I'll do a probe beam far field. So this will take now, let me do it, this near field pattern, which is lining up pretty well with that. I might actually drop this even down a little bit more and regenerate that. So this near field pattern, and if I wasn't compensating it, it would kind of look like this, but with the compensation, I brought it back to a nice clean spot. Okay, so we have the phase control working here, but you can also do slope control, and this is what you do most typically with a Shack-Hartmann wavefront sensor. I almost always end up removing a mode, so I'll start with that. Click on fit the gradient, and now we can take a look at these matrices. This is the poke matrix. it looks like two matrices that were concatenated because we've got the X terms all on the left side and the Y terms all on the right side. So it's an XXYY configuration. You can do XY configuration and it'll look more like the poke matrix from Phase, more diagonal-ish kind of a matrix. But for this software, we decided to do the XXYY, and that's why you get these sort of almost two concatenated diagonal matrices, or diagonal-ish matrices. Let me look at the gains for this. Yeah, there's always, it seems like almost always one mode that's really low, and this is oftentimes a waffle type mode. You can see that if you want to take a look at it, you can go to the DM SVD modes. The waffly mode is definitely the case for a free geometry. Now that we're not in free geometry, it may not be that. Yeah, it's these edge terms that are problematic. You can see that in by looking at the SVD modes. Okay, so I've eliminated that. Here's the aberration and here's the fit to that. This is not the prettiest control matrix I've ever seen. It's showing the diagonal-ish components here, looking kind of like the transpose, but you've got a lot of content that is problematic. But it is producing a decent fit and a very good-looking residual. If you want to see a numerical analysis of that, you can see it on the Analysis tab page. And this is text you can cut and paste into other documents. Peak to valley, we started off with 1 micron. The fit was 1.25, and the residual got down to 0.6 peak to valley. The RMS is a little more impressive here. Again, 0.2 on both the 0.223 maybe for the RMS aberration, 0.27 for the fit, and now we're at like 9 times 10 to the minus 5 millimeters. About 90 nanometers for the residual. So it's looking pretty good. Again, evidenced by the fact that this far-field spot looks quite good. Okay, so we have designed a DM, done a wavefront sensor overlay on that, so we have a complete AO overlay, generated aberrations and fit them. You know what I didn't do was any of the Zernike terms, so let's just do that real quick. Click on compensate with phase. So lots of high frequency residual left in this one. Compensate with the Hartmann sensor. This one actually looks a little better, again, except for at these very edges. You could also take a look at the probe beam far field and the compensated far field. So it's doing a good job of compensating that in terms of putting light back into this diffraction limited spot. Okay. There's a couple other features that I'll talk about on here briefly. One is this create Zernike fit matrix, and what this does is go through and try to fit the DM with a bunch of fit a bunch of different Zernikes with the DM and wavefront sensor overlay. This produces a fit matrix that is nominally diagonal, but then the off diagonal terms are showing you about the coupling between the other modes. So this is nominally a diagonal term, but you can see that when I'm trying to create what I think is the spherical aberration term, I'm getting a lot of focus showing up there. And so if you wanted to check that, you could go in here and say, okay, let's make that 0, and go down to spherical aberration here, and let's see what a micron of spherical aberration looks like. Okay, and then the fit to that. Oops, I have to click the AO fitting here. Let's do the Hartmann version. And so there's the aberration and there's the fit. That's not terrible, but the residual has a lot of edge content, which is producing a focus like Zernike overlap. Okay, that makes sense. Okay. We've looked at influence functions. This is just showing a color version of the actuator mapping. We've talked about all of this. Let's move on to this continuous display mode. So let me click on continuous here. What this does is go through and generate a random realization of Kolmogorov spectrum turbulence and show how well it can be compensated. So let me click on laser spot, and so what this does, and this does a lot of funny stuff here in the beginning here because it's creating a movie and it needs to display all of these. Once that movie's done, it's getting through these frames, which you can just set to 0 if you don't want this to happen. You can go click on continuous and just see on a continuous realization, this is what the probe beam would look like off the DM, and then this is what the compensated beam looks like. So you can see that it's doing a very good job of compensating this slight amount of warp we're getting from Kolmogorov spectrum turbulence. Okay, so I can stop that. I did say it produced a movie, and so in the background here, we can go back to the list of files, and this is the movie that comes out of that. We're working on the scaling of this movie right now, but what you can see here is the probe beam intensity, let me just pause it here. Probe beam, diffraction limited, I'm sorry, the far field, which is nominally a diffraction limited spot after it's been compensated, the aberration we're trying to compensate, and the best fit that this DM can do to that. So you can produce a little movie of this. Working the scaling on this now. It's a new feature for us. Okay, so now we can go back to the AO simulator, and we can do an image mode version of this as well. So instead of just looking at the laser spots, we can convolve that with an image and show what the effect of the atmosphere is going to be on that image, and what it looks like corrected. This is a pretty weak atmosphere relative to the DM we're talking about, and you can see that it's a lot of tilt term. It's been stabilized by the AO system, but it's also, there's some blur term in there as well. Let's stop this and go into here and increase that. I think I had it set to 18 before. Let's try that. Go back here and say start. Load the image again. There we go. So now we can see a little better. This is what the aberrated beam looks like, and this is what it looks like after compensation. We still have some blurring happening, but not nearly as bad as it was corrected when it was corrected. So let me just run this again. Let me get through about 10 of these, so it'll create a movie. That looks good. Stop this here and go back to the directory here and go to the top, and it should have created for us an AO image demo. There it is. And so this is that movie, so you can put these into presentations and show compensation. Okay. All right, so what else can we do with this software? We can do beam shaping with it, and so I can define a shape of a beam or load a shape. And I'm going to say, let's try to create a, let's see, these are the orders. So I'm going to make this like, let's keep it 10th order. Let's try to make a line focus. So we're going to say 10th order, and we're going to make one axis 4 and one axis 10 or something like that. Refresh this. Oh, 4 looks like it's a little too big. Let's make that more like a 2. Refresh that. These are radii, so let's keep it small. Okay, this looks pretty good, and I'm going to try to make that that intensity profile here. Okay. Once I've defined a shape, the next thing I can do is just say shape the beam. And so what this will do is, let me stop this again and restart it. Yes, use the prior solution. This will go through and poke on actuators in this case in symmetric patterns, and try to create this line focus for us using this DM. And so it's using a stochastic axial search pattern. You can see it's converging in here on a more line type focus, but it takes into account all of the physics to get us there as well. So this is going to be a realistic estimate of what's happened. I'm going to pause the movie here so that this can converge, and I'll be back. Okay, so it is now converged, and it's showing us a line type focus just like we wanted. We could let this continue and probably get a little bit better, but for a demo purpose this looks pretty good. It's also showing us the DM commands required to get us there, and the search parameters and some of the other settings about convolving with super Gaussians. This is useful when you're working with a laser with pretty low beam quality, and so if you're trying to shape a laser with low beam quality, you can approximate that by convolving it with this super Gaussian. Okay. This settings tab allows you to save your setup and load your setup. And so this gets you back to where you started in terms of all the settings throughout the document, throughout the program. You can save the results in the AO configuration. We've got a couple of exporting capabilities to PowerPoint and to MATLAB here that save a lot of the generated data out. You can save the actuator patterns out and the wavefront sensor patterns out. You can use on the overlay plot, you can use a click action in order to remove actuators if you wanted. I'll just demo that real quick. And you can also clear the actuator removal. So you can eliminate actuators if you wanted to create an unusual shaped DM, but you can also just load those if you have an unusual actuator pattern you wanted to try. Okay, this aberration scan shows us if I have a given aberration, let's say it's the spherical aberration, how does that impact the intensity in the image? And so it's, it always does a 0 aberration case to show you what that looks like. It's nominally 1-ish in terms of power into buckets and things like this, and then it shows you what happens as you scan it. I'm going to drop this down to 0.1, rescan this so I get a few more points down here. There we go. And so you can see this nominal Gaussian-ish start to the shape here, which is expected from the Marischal approximation. So you can take a look at how an aberration will impact the power in a bucket and the intensity. Okay, so this is a brief introduction to the AO simulator software. It'll allow you to design up DMs. If you have features you want added, please don't hesitate to give us a call or send us an email, and we'll see if we can get those in for you. And you can download this from the AOS SharePoint. Thank you very much for your attention, and let us know if you have any suggestions.